Hi, everyone, and welcome to part 3 of this video series on the paper by Jean-Charles Rochet, a necessary and sufficient condition for rationalizability in a quasi-linear context. So in the previous parts, we covered the main theorem, the statement and the proof of that theorem. And in part 2, we covered the single-dimensional case and the characterization of the rationalizable mechanism in that special case. Now we are going to take a look at the multidimensional case, in the general multidimensional case, but more specifically and more closely, we will take a look at the linear case. So in the linear case, the value function t and x is going to be, so these are going to be vectors now. And those vectors would belong to their corresponding spaces of dimension k. So it's going to be a scalar product t, scalar product x. I'm going to drop the vector notation. This is just to explicitly remind ourselves that this is what it means in the multidimensional case. Now, in this particular case, the statement, there is additional statement we can make that would characterize those rules X. In particular, the X is rationalizable if and only if there exists a scalar function and it's going to be conveniently called v of t. So the connection is pretty obvious. This scalar function such that it is convex, and then the statement is that the x of t belongs to the subgradient of v of t. And actually there is a slightly more general statement, but we will take a look at it later. So here we have x of t. I just want to mention the connection to this more general statement is that x of t here is actually a gradient with respect to t of v of t and x of t. Well, this is very simple. It's just t scalar product with x of t. So, well, the gradient of that would be right. So let me just move this thing a little bit to the right. So, well, the gradient of that with respect to t, this is like an explicit gradient. So not taking gradient here on this part, this is going to be x of t. Okay, so how can we prove this? Well, to get the proof, we will first need to recall the definition of the subgradient, and then using that definition of the subgradient, we will be able to connect it to the taxation principle that was explained in the part 1 of this video series, and then it's going to be pretty clear. So let's take a look at the definition of the subgradient. So okay, I will just this is going to be a proof a little bit later, and now we are going to take a look at the definition of subgradient of a convex function. So this is the following. We are talking about the scalar function v of the vector argument t. And again, I'm going to drop the vector notation from this point. So the convex function and its subgradient are connected in the following way. So a little bit differently. The subgradient of v of t is a set. First of all, the subgradient is a set of numbers y, actually vectors y, such that v of t is greater or equals than v of some t prime, some other vector, plus scalar product of y and t minus t prime. For all t prime in the domain of the original function v, so belonging to this domain of v. I guess it's there is some assumption that the domain is also convex. So now, how can we use this to do our proof? Let's see. So first, let's assume that we have a rationalizable mechanism. And we want to prove that V is convex and x of t belongs to the subgradient of V of t for all t in the domain. Okay, so remember that rationalizable also means that we can use this use the taxation principle, and the taxation principle tells us that the utility, this V of t, is going to be the maximum over some menu of options. And this menu of options is going, in general, look like t and x j minus p j, right? So, well, in this particular special case, in this linear special case, we have the max over the set of options in the menu of t and x j minus p j. So from here, we can immediately get that V of t is convex as an upper envelope envelope of a family of linear functions. So the visualization here is pretty simple. So let's take a look at it. Let's consider a convex function, something like this. So actually, I wanted to go from the other direction. I want to first draw a family of linear functions and then draw the envelope. So the family of linear functions would look something like this. Is going to be a linear function going like this, then we could have, I don't know, another linear function going like this, another linear function maybe going like this, another linear function going like this, and then there is another one, let's say, going like this. So from here, we take the envelope, and the envelope is going to go, I'm sorry, here, then it's going to go here, and then it's going to go here. So it's pretty obvious that the envelope of the upper envelope of a set of linear functions is convex. Okay, so now we can use this to also show that now we want to show that the x belongs to the subgradient of v of t. Okay, so how can we do it? Well, we have v of t greater or equals, according to this, greater or equals, then some t in x, the one that is the best one, right? Well, for any other one, it's going to be greater than equal. So for any other t prime, it's going to be minus p of t prime. And then remember that for p t prime, we had this definition that it's going to be v of t prime x of t prime, right, minus p of, no, minus v of t prime. But also we are considering a special case, which is a linear special case. So this thing is actually linear. So this is a scalar product like this. And well, what we get, v of t greater equals, then yeah, we should substitute it there. So we will get v of t prime plus t t and x of t prime minus minus t prime x of t prime. And yeah, and we get this v t prime plus we get the x of t prime and t minus t prime. Right, so let's compare this. Let's compare this to the definition of the subgradient. Here we go. We have exactly the same thing where we have x of t prime here. And this means that, yes, so this is what we want to prove. So this is the subgradient. So x of t prime is a in subgradient of v of t prime, right? Let's check it again. Yeah, this should have been like this. So we are actually considering all the, so this is going to be some t prime. And for all other t's, the components, those linear functions that define the subgradient, they lie below this. So this is t, right? So this is x of t prime. Actually, this is v of t prime, right? Yeah, so I hope it's clear that this is the correct definition. That there should have been like a switch of this t's and t primes, but it makes sense. Okay, so we got our proof that if we have a rationalizable mechanism and with a linear value, then we get our indirect value function, indirect utility being convex, and also the allocation rule belongs to the subgradient of v of t, and in the sense we can also say that v of t is a potential. And here we have this is a special case of the envelope theorem. Theorem again. So remember the envelope theorem is saying that whenever there is an optimization involved into defining x, then when we are taking the derivative, we don't really need to consider, we only need to consider like the explicit derivative. So this is basically saying that well, it's in general like this, that the dv by dt, where this means this is going to be like gradient with respect to t of v of t and x, of v of t and x of t. This thing belongs to subgradient of this v of t. And also there is an integral formulation for this. So the integral formulation for this is extending the one-dimensional integral formulation that we had in part 2. But now we need to consider, let's consider for the visual, we can consider two-dimensional domain. So this is going to be T1, and this is going to be T2. So imagine now there is a function v that is above this plane, or like this is the domain, and then there is the scalar function. So like the projection of those corners of this this function is convex. So the projection of it would look something like maybe something like this. So there's going to be like a convex projection where the slope of this v is changing, because remember v is an envelope of linear functions. So it could, I don't know, probably could look something like this. Something like this. So there are zones, and this is specifically relevant when the x of t is piecewise constant. So now if we take an integral from this point to this point is going to be the point called t. So this is a vector. So, okay, I will actually erase this one. This is a point t. This is, let's call this t0. Then the integral over any path from t0 to t of this v of t and x of t. So this is again the gradient with respect to only the first argument here times dt. Now dt is a vector, so this is actually like a scalar product here. Because we just proved that this thing, especially in the linear case, this is going to be gamma from t0 to t, and here we have x of t. Well, the notation is not perfect. I would say it needs to be like a different variable of integration. So let's fix the notation here. It's going to be s ds. So again, this is a vector. This is also going to be a vector. This ends up being, for the linear case, we showed that this is going to be x of s ds. And because this is a subgradient of a convex function, we know that it's this convex function is differentiable almost everywhere. And the integral does not depend on the path. It just depends on the starting and the ending point. So this is why the capital V is a potential. So we can integrate maybe along this path. Maybe we can integrate along this path. But there are a couple of practically useful paths here. One practically useful path is just a straight line. Yeah. And another practically useful path is along the axis. So we can go here. We can go there. Like this. And we can also conclude that this condition of rationalizability also means that an integral over a cycle, yeah, like this. So if we go like a full cycle, the integral of the full cycle is going to be 0. So this is the property of this of the potential functions. And in the paper, the statement about this is basically given in the differentiable in the differential. So it's like the rotor of this gradient of right. So basically the rotor of x of t is 0. So that is the condition. Assuming that x of t is monotone in the regular cells. Right. So to complete the proof, we need also to take a look into the other direction. So what if we have that there is a potential function v, and there is the allocation rule belongs to the subgradient of this potential function? How can we prove that the x of t is rationalizable? Well, that is pretty straightforward. So the other direction from convex v of t, this is convex, and x of t belongs to the subgradient of t. Prove that x of t is rationalized. Well, here we go in the other direction. So we again use the definition of the subgradient at point t. So the subgradient at t is going to be greater than equals. No, the subgradient at t is going to, at the subgradient of at point of t prime is going to be equal to, this is like the definition of subgradient. So we have it here as t minus t prime, okay? And if we just define, if we define the payment in the usual way, which is P of t is going to be V of t and X of t minus V capital of t. And in our special linear case, this is going to be just a scalar product of t and X of t. So let's see. Here we have V of t is going to be V of, so I'm first going to expand this thing. So it's going to be V of t and X of t minus P of t. Right, is greater equals than, now we have here V of t prime X of t prime minus P of t prime and plus this thing and t minus t prime. Well, we are still in the linear case, so we can also replace it like this. Greater equals t prime X of t prime minus P of t prime. So this is going to be plus t X t prime minus t prime X t prime. So this is going to cancel, and we end up with our usual rationalizable definition that so what we proved is that there exists, in this case, there exists this function P of t that could be defined in this particular way that would make this allocation rule rationalizable or truthful. So one last remark here, and again, this is the last statement of the paper itself, that the necessary condition is quite general. It says that, well, yeah, if X of t is rationalizable, then we have this gradient with respect to t of V of t and X of t belonging to the subgradient of V of t. I guess well, no, in this case, this is a more general statement. So this is this could be, this is probably saying that in fact this is using the taxation principle, we would go with let's check it again. So the taxation principle is going to tell us that it's a general statement. So we this v of t is the maximum of in the menu of v of t x of, well, j, right, minus p of j. And because of the envelope theorem, we would get this more general statement that v of t minus some v of t0 is going to be this integral of gamma from t0 to t 1 of this v of this gradient with respect to t, and yeah, x. Okay, let's use the s as the integration variable, ds. And for this to make sense, for this integral to be like uniquely defined, and it should not depend on the path. And this is like basically the what the cyclic monotonicity gets us. And then I guess the same condition could be written as that since this integral does not depend on the path, the rotor of this gradient of v of s and x of s should be 0. Well, this is it. Here we conclude our exploration of this paper. And if you find this useful, if you have some comments or corrections to what I was saying, please leave a comment. My notation and my proofs are a little bit sloppy, so I guess reading a paper and checking the contents of the paper for yourself would be a very good idea. Thank you very much for listening, and see you next time.